Welcome to your last lecture video for MET 103. This will be relatively short, admittedly, for the folks in the early morning lecture. A little bit of overlap here at the beginning just to make sure everyone's on the same page. So either bear with it for the first few minutes or start skipping forward until you see the slide that looks new to you. So again, we're wrapping up our lecture on global climate change, and here the idea of the fact that we just went through a series of maps showed that there is some warming that's occurring on a global scale. We brought up the facts that we see this more commonly at the high latitudes. We see this over land. And so the other thing is that it's not simply just atmospheric warming. We're seeing some other changes that would be coincident with things related to this warming pattern. Things such as, where do storm tracks occur? Do they maybe occur a little further north than they may have otherwise due to this warming? Various atmospheric circulations, small changes, but things that again would be consistent. Some of the more tougher things to really understand in the large scale, such as water vapor, feedback mechanisms related to clouds. We'll talk about that a little later on. And then again, things such as sea ice, which we just spent a notable amount of time towards the end of lecture on Wednesday. One of the big takeaways truly from this section is the fact that we cannot explain the warming that has been occurring over the past number of years simply by natural occurrences. Again, we've talked about things that we as humans do have control over, such as the release of a number of greenhouse gases, and other things such as volcanic eruptions and orbital changes. And so if we simply look at the natural features, it may explain some percentage of the warming, but not all of it, and that becomes one of the biggest issues at hand. And the idea furthermore is that the climate is likely to continue to warm. The oceans that are warming as well hold a lot of heat. Again, related back to the concepts of specific heat, the fact that they warm slowly, but then also retain their heat for a considerable amount of time. Combine that with the fact that there's so much more of Earth that is covered by deep oceanic waters, means that it's really hard to reverse the trends in the oceans at a rapid pace. And so again, we're simply absorbing a lot of heat energy, and it's not to where this is very quickly eroded. Looking at greenhouse gases, again, this is not my schematic, so I accept zero responsibility for dioxide spelled incorrectly. Again, note the y-axis showing a baseline of 250, so even though there is an obvious significant increase over the number of the years, it may not look as extreme if you had a different type of y-axis here. And so you can see here a number of gases, carbon dioxide, methane, and nitrous oxide, ebbing and flowing through, the first 1500 years AD, starting to tick upward maybe towards, the middle of the 18th century, the idea of a lot of industrialization in a number of nations, including the United States, and then an incredible uptick that we've seen in recent years with regard to all of these different concentrations of greenhouse gases, again suggesting that there is a notable anthropogenic or human influence on the changes in our climate. And so this would have been the slide that we ended off in A, and so we'll be on the same page after this. This is a very important slide. What you have here is three graphics, the one in the upper left corner indicating if we only looked at natural forcing, the one in the upper right corner looking if we only looked at anthropogenic or human-influenced forcings, and then at the bottom the combination of the two. So in all of these traces you see a red line, again a lot of variability from year to year, and that red line is identical between all three of these charts. What's different is what is underlying in the gray. You see model results based upon natural forcing. Here in the upper left, see if I can get my cursor out there, you can see catches some of it, but especially in recent years does not explain what we're seeing in the observations. Anthropogenic forcing does a little bit better job, but let's be honest, still misses some of the signal. But when we combine the two, the idea of what is happening that we have control over and what we do not have control over, we really fit the model and the observations quite well, suggesting that when we start to tackle the problem of global climate change, we really need to make sure that we're accounting for all factors that may be influencing things. And so one of the obvious, very natural questions is, where do we go from here? What's going to happen moving forward? And so what you see in this image, again, the models in and of themselves, it's not important for you to understand any specific models. What we can glean here, though, is there is no pure agreement in what is going to happen moving forward. What we can see is, depending on how much in terms of the model with regard to feedbacks, for instance, the RCP 8.5 shows a significant warming that's expected to occur over time, whereas relative to the 2.6 model here, again, these are just different trends. You can see some of them show a 4 to 5 degree warming from around the year 2000 moving forward to 2100. Other ones show a significant leveling off by the time we hit the mid portion of the century. Some of this is related to these feedbacks. The idea that we have certain mechanisms such as the sea ice with the albedo, that's a positive feedback, and that's going to continue to build on it. But there's other feedbacks that are more negative in nature. The idea of if we continue to increase water vapor, which would be expected if we are continuing to warm, thinking again back to our Clausius-Clapeyron curve, how much moisture can we hold at different temperatures, the fact that this is also going to potentially mean that we get more clouds. And what happens if we get more clouds? Does that start to block more of the incoming sun and therefore decrease our warming? It's a little bit of a conundrum moving forward. Regardless, it is expected to see temperatures continue to warm based upon temperatures in the late 20th century throughout much of the later portion of the 21st century. So you can see here these are some expected values from 2090 to 2099. Seems so far in the future. It's important to note this, that between some of the charts that we've seen from recent years and even more here, we see a couple of pretty strong signals. We see that the warming, regardless of the magnitude, is expected to be much, much more intense at the high latitudes. In other words, near the polar regions. Furthermore, you can really see this over the northern hemisphere, that the land masses are expected to warm more rapidly than we see over some of the oceanic waters. Again, what we have here is the fact that land can heat more quickly than some of the surrounding water, and so if we have year on year of some type of warming, that's going to be realized much more easily by land masses than it will by water. Precip. Again, the fact that we are expecting a global rise in precip should not be surprising. The fact that we have warmer temperatures expected, warmer temperatures will be able to hold more moisture. These can produce more clouds, and therefore, in general, more clouds will equal more precipitation depending on the depth of atmospheric moisture and the other processes at hand. You can see that we're really, again, looking at the greatest influences, again, percentages here, occurring near some of the highest latitudes. We can see some interesting influences near the equator, not far away from the ITCZ, but then you also may note that near some of our subtropical high latitudes, these areas, maybe North Africa and Europe, stretching down into portions of the Atlantic, similar signal over the southern hemisphere suggests potentially a mild decrease in precipitation. This makes this a little bit harder to project what is going to happen in very specific regions. This has significant ramifications. If we simply warm things up, we are already causing some changes in what we might have for biomass in certain areas. But if we start to also alter the amount of precipitation, we may significantly change what types of crops grow in which regions, what happens to some of the world's deserts, so on and so forth. But one other thing that's very important to note as we continue down the path here of global climate change is that not all models are the same, and there is always going to be some type of year-to-year variability. So what we have here is just showing how if we had model simulations over the past number of decades, we see our temperature anomalies on the left, and we see our black line showing the overall increase that was expected for a number of years. But what you can see is that even though there is a general upward trend, that does not mean that every single model is going to be spot on. It also means that some years are going to be warmer than others. We saw this in the example earlier between March 2012 and March 2013 over the Chicagoland area. Even if we're in an upward trend, we can still see years in which we are notably cooler than typical. But when we look at climate, we have to focus on that long-term signal. And so where is the debate moving forward? What are the future influences of our changing climate? It is quite possible that we see continued warming. One of the things that will definitely influence the rate of warming is the emissions that we have here that are anthropogenically driven. Some areas, as alluded to earlier, may simply become too warm to grow food, and this could be further complicated by precipitation changes. You may, though, open other areas to different types of crop growth. But ultimately, if we start to change or alter the global climate notably, we are going to see certain populations, whether it be for plants or even some type of animals, become extinct because the adaptation to climates, even a degree or two, can be very significant for some sensitive crops and animals. It is not outside the realm of possibility that we continue to warm, but that we actually lead to a cooling, related to, again, things such as water vapor and cloud cover. Still, these may start to result in some areas that have different patterns of crop growth, different types of environments to support animals, and regardless, these changing climates are going to change that people and society in general behave on planet Earth. Thus ends your lectures for MET 103. This will be available on YouTube, as you already have likely seen, unless you are clicking through Blackboard. I hope that viewing some of the things via video through this class have indeed been helpful and maybe ease some of the burden of coming to class. By all means, if you have questions, feel free to reach out. I hope you've enjoyed some of the lectures over the semester. Take care, and see you soon.